Welcome to the Stumbling Spirit, contemplations on the path of resilience. Whether you realize it or not, you are resilient. It's your birthright. As you take in your next breath, know this truth. It's not only about your capacity to overcome difficult situations, but it's about your courage to do the necessary work to heal, learn, grow, and move forward. What you gain is invaluable wisdom. And it's through these hard stumbles in life that we often discover a new purpose that aligns with our spirit. My name is Fabio da Silva Fernandez, Reiki Master, Mindfulness Coach, and Mystical Explorer. Join me weekly as the Stumbling Spirit podcast highlights the lives of extraordinary people like you, sharing transformative stories and beneficial practices of resilience to guide you on your wellness journey. It's estimated that there are over 3 trillion trees on this planet, with 842 million hectares of forest in South America alone. One of these gentle giants is said to be the oldest in the world, nearly 5,500 years old. Gran Abuelo, or the great-grandfather, is a Patagonian cypress located in Chile. As a child, Jonathan Barichivich marveled at it, and now, as an environmental scientist, he studies it and other trees like it, not only to decode their ages, but to reconstruct the past and predict the future impacts of climate change on Earth's critical zone. Jonathan is here to discuss his important research. It's a pleasure to welcome to the show research professor at National Center for Scientific Research in Paris, associate fellow at Norwich University, and European Research Council laureate, Dr. Jonathan Barichivich. Hello, Jonathan.
Hello, thank you very much for the invitation.
Before I get started, I just want to mention that the tree stats that I got was from 8billiontrees.com, and my background research for this interview comes from BBC, Al Jazeera, and content directly from Jonathan Barichivich's website. The first thing I want to discuss with you is Gran Abuelo. How were you first introduced to this tree as a child?
That's difficult to pinpoint an exact moment, but since it's been always in my reality in a way since a kid, so I always knew it. I always knew that it existed, but probably I have never thought about how singular this tree was in the whole planet.
I'm just curious, because obviously the tree was in your direct environment. Were there any legends about the tree? Was there any lore about the tree when you were a kid that you can remember?
That's a bit of a surprising thing I would say about this particular tree, a very ancient tree, is there is not much knowledge about this tree. And since it was very isolated from people, there is no contact with native people either. We are not aware of any native people that had met the tree before or anything like that. So it was really hidden marvel from humanity in a way of nature. It's one of the characteristics I would say is that we know very little about this tree.
I'm assuming that there was something that made you notice it, though. Like, what sets it apart from the other trees in the environment?
Well, it's just its presence. When you are around the tree or you approach the tree, you just, you look at it and it's just very old looking, with burls and very wavy trunk and not as a typical tree because usually very ancient trees are very they don't have the typical shape of a tree, so it's just its presence I would say, and its environment where it grows. It's in a valley that around a river that make a sound and that surrounds you like the sound of water running, and that when you are approaching the area where the tree is like half of the slope more or less into the valley on a rainforest, so a very very dense forest, you're just involved by this surrounded by this sound and atmosphere that's really mysterious in a way, so its environment is also very unique.
You just mentioned the environment, so can you maybe talk about the geography where this tree is located in Chile?
Chile is it's a long country along the west coast of South America, so we are talking about around half of the country. So first is the desert, then is the Mediterranean region where the wine is produced, then there is the Valdivian rainforest, and then there come the fjords to the south where the coast breaks into fjords, and so we are in the Valdivian rainforest, so in the almost southern half. And there, this coniferous species, which is Alerce, grows in the Andes Mountains, but also in a small coastal range near the Pacific coast. So you have the Pacific, then you have a small mountain range that peaks at 1,000 meters, and then you go down towards an inner valley like California in a way, and then you go up in the again in the big Andes. So Alerce grows in the Andes. It used to grow in the Central Valley, but it was basically destroyed there. Basically, there are just very few forests that remains. And then in the coastal range. So this is located in the coastal range where the clouds really come from the Pacific, hit the mountain and discharge big amount of rain. So we are talking about 5 meters to 7 meters of rain per year. So it's very rainy, but in the summer it's sort of dry. So we have like a dry season and a very wet season.
I guess I'm assuming that for this species of tree, that it's an optimal condition for it to grow and thrive.
Yes, it would be equivalent to where the westerly winds bring the storm track, so around 40 degrees south, which is more or less equivalent to, let's say, to Washington or that type of rainforest. So very cloudy, very wet environment, and very also coastal climate, very humid.
I'm just curious, was it just coincidental that you studied this tree as an adult, as a scientist, or was it intentional for you to study this tree?
I think it's difficult to say because it's in a way the tree was always there, and it was always the story I have with the tree and with my grandfather, my family growing up in a national park. It probably is the inspiration of my career, or was the thing that really there is a sort of fate, I would say, that I will come, make the full circle and come back, go away from there because I had to go as a kid to go to the school. This is a very remote area, so I had to go to the lowlands to go to the school. So I have to leave behind my family, my grandparents in the mountain, and just since I started to study, I would just go in the summers basically, and in the winter breaks as well. And then went away to Europe to do my PhD studies and master, and then came back eventually to the same point and came back as a full scientist, and but still not working with the tree itself, but working with the forest in the park. But fate in a way took me to work with the tree because as I said before, we know very little about this really wonderful being, and it was in very bad condition when I came back around 2016. The over tourism has really had a negative impact on it, and people would walk around the tree and the erosion. It was just really advanced, and so the roots were exposed, and then people would trample into the roots, and will produce a tremendous damage in the last part of the tree that is alive now, which is just it's 1/3 basically in the upper part of the slope, and where is the people go and take pictures. So I had to do something, and that's how with a colleague and friend Antonio Lara from Universidad Austral, the nearest university, we took a sample, and then basically we arrived to the estimate of the age, but that was not the aim. The aim was to really look into the tree rings and see how the tree was feeling the climate and all the changes that are occurring now there, which is this rainforest that is drying out in a way, and to see how the tree was feeling it. And that was the main objective of our initial research with this tree.
So it was coincidental then. You wanted to basically check on the health of the tree. And by doing that, you took this 1 meter long sample. And when you study the tree rings, you're like, oh, this is a really old tree. So when you extrapolated that the tree was 5,000 at the time, 5,484 years old. When you extrapolated that, were you amazed, shocked? Like, what came to mind when you discovered this information?
Yeah, so it's in a way the age still to me is not important. It's still is an estimate, and in a way there is something to it that when you are in front of such a being which is very ancient, if it 3,000, 4,000, 5,000, 5,400, 100, whatever, it doesn't matter. It's just age is a number that humans measure, nothing else. It's really beyond a certain point. It's just a miracle in a way, something that you rarely see in nature. So it's just a symbol of endurance, and so it's something beyond just a number that you cannot compress all what the tree is in into a number. So it's impossible with just one number as the age. So for sure, it's one of the oldest trees alive now in the planet. But also there is a nuance to it because there are different type of trees. There are these trees that are clonal, like pando, this popular tree that is like a 50-hectare tree in a way. It's just a giant clone. And so, but the individual stems are very young, 50, 60, 80 years old. But here we are talking about a single stem tree, non-clonal, that has been standing in the same place and in a way being living the planet for such a long time. So I guess here is where we start to approach the limits of science when we go to that. That's why I'm telling you that one just can't simplify it just very old. You cannot say 4,800 or it's because you cannot count the rings. You will never have all the rings. Also, in a way, at the end of the day, it doesn't matter because beyond that point, it's just very old. And also, it's just a mystery. The whole life of the tree will remain a mystery in a way. A big part of the tree will have the last 2.5 millennia of history in the rings, but beyond that, we don't have. And to be honest, I don't want to have it either. I guess it's a mystery, and there are parts where at this time, it's not our role to dig into that. And I think also it's just the attempt to estimate the age, to use science in a way to get an answer without touching the tree, in a way just by asking without being too invasive. It's a scientific challenge, but it has uncertainty, and we approach to the limits of dendrochronology, which is the science that use tree rings to age trees and to study how trees respond to climate. So it's beyond the boundary of what we can do now, and I think is the most wonderful thing that I have learned by working with very ancient trees. There are just mysteries you cannot solve at this time.
Just for our listeners, when you say that beyond 2 millennia, it's a mystery, it's because you were only able to take a 1 meter long sample, but the tree trunk's width is 4 meters. You can't go any deeper than the 1 meter. And so it's very hard to know about the history of the tree beyond 2 millennia. Is that
Yeah,
fair to say?
yeah, it's in part is because to get to the theoretical center of the tree, we will have to go still with another meter to get the 100% history of the tree. But the inner part of the tree might be rotten away, so that history basically is gone. And I wouldn't dare or I wouldn't let anyone bring a massive borer and take a big core of the tree because that thing can break. The shaft of the board, the bit in a way can break, and I could not live knowing that you have left like a piece of metal forever inside a tree, inside a being like that. So there are many ethical considerations, and also it's about the meaning of the tree or its existence. And so I think going back to the point where you asked me if there were legends, About that tree, I think we are starting to unravel the legends right now. They were not there, as far as we know, but I think the tree has started to talk to humanity just now.
And by that, you mean the rings, the tree rings are telling a story about what the tree lived through.
Yeah, but also what the tree has to go through in the future, and the meaning that it's being alive today, and why we know nothing about the tree, and why we, in a way, we did not know the tree before. So its message start to be read just now, basically, in our human time, just a few seconds ago, in a way, for the tree, but I think it's a difference with other ancient trees. There are ancient trees that we don't know that they exist, which is great, I think. But there are some others that we know that they exist, and they might have some legends, they might be known for people, but this one in particular is, in a way, talking to us just now. And I think some people is starting to really understand the meaning of this being, why it's there, why it's been silent for so long, and why it's coming to talk to us right now, in a way, through science or any mean of perception that we have. And I think that's a particularity of this tree. So it's a story that is just unraveling in our times.
I really resonate with how you describe Gran Abuelo in terms of the fact that you have a reverence for this being, as you say, and that you really do feel the presence of the majesty of this tree. And it's great to hear from a scientist. Maybe it's just a stereotype, but it doesn't sound like scientific language, but it's great to hear you say that.
I think with natural history, sometimes, rarely nowadays, we can see natural history as going back to the mystery of life, in the universe. So this tree is more precious than diamonds in the whole universe. If you think this living being is one of the most precious things that the known universe has at this time, and is still there. So it's just unique. And I think when you look at life in the wider perspective of the universe, and life in the universe, and then what it means to keep alive for so long, with all the laws of biology, with the chances of catastrophes and many things coming through, it's just wonderful in a way. It really means something, and I think when you talk about the natural history of these trees, you go back to really the keys of life, the meaning of life in the cosmos, like in the wider perspective, and the frequencies at which these beings live at millennial frequency. It approaches to cosmic times, like we are not gonna see a comet like in 300 years or in 400 years, and the tree can still see it many times. And the Halley comet, like around 70 times probably this tree have seen it passing by. So it's really at cosmic frequencies. It's way beyond what we can experience as humans.
Let's talk a little bit about the origins of life for this tree. What do the tree rings actually tell us?
In particular, it's just every year, more or less, in a seasonal climate, be it because there is a fluctuation in water availability for plants, or in the optimal temperature for cells to grow. In a way, in this case, is because of temperature, basically. So you have a cool winter, a mild spring and summer. So the cells, cell by cell, develop around the tree in an area. Is like a sheet around the tree, or a cone. If you stack several cones together, basically is equivalent to put 1 year after the other of growth, and then you cut through the cones, and then you will see the individual cones as rings. So that's basically a tree. So our cones stuck together, but the width of each cone layer, it's about 50 cells, more or less, 40, 50 cells. And every year the tree will form a layer of around 40 cells, but sometimes it can be up to 3, 4 when it's a very cold or dry year. So how these cells, how many they grow, and the size, and also the chemistry that is used from the in a way the tree used to build these cells give us clues of the environment, what was the environment that the tree experienced. So very small cells, it means that the tree was being stressed, and probably if it's in the summer it would be drought, and so drought will in this tree in particular would lead to less cells and also to smaller cells. And then we correlate the ring width, so a whole ring width, or a true ring in a way, a whole true ring, it's just the width of these 50 or 40 plus cells that are formed every year. So it varies. And that variation, that width, is the simplest measure for a tree in a way, the width of every ring through all the depth you can go into the tree. And in this case, 2,465 years, you will have a measure of how the tree was feeling the climate. So less growth, it means more environmental stress. More growth, it means more optimal conditions. So, but then there are many metrics now that we can extract. So as I said, like there are the oxygen and carbon isotopes in tree rings, basically that are molecule of carbon and oxygen that are not all the same. So there are at least two types that we use, and it's like in a way at the level of atoms or molecules. In a way, it's like having candies, and there is a flavor that we like and a flavor that we don't like. And in a way, the proportion of the two flavors in the wood of the tree tells you about the environmental stress. Specifically, you can infer from this chemistry of carbon isotopes in particular, carbon 12 and carbon 13, the fraction of the two tells you how the stomata, these pores that plants have in the leaves, were open or closed. So they close when there is stress, and they open when there is not stress. And basically, when they open, they transpire, allows the water to leave the leaves from the soil to the trunk back to the atmosphere, but also they capture the carbon from the atmosphere for the photosynthesis. So the proportion of those can tell us a lot about the conditions and the physiology of these trees back in time. And knowing that, which is a very specific knowledge of the response of the tree, we can also infer how the trees might respond to the future climate, because we have a very good idea now with climate model projection how the climate is going to change. So we really can, by knowing the past, we can really predict much better the future. And that's the trick in a way. That's how we can use the science of these trees really to inform what the future of these forests is likely going to be. So it's that's the part, the scientific part that I am addressing in a way at this time.
So, what you're talking about is you are using the tree ring data, including the carbon isotopes, to reconstruct the past history of the tree, what the tree went through, but you're also trying to model what potentially might happen in the future. And that's what you use this data for, and that's part of the research that you're doing right now.
Exactly. So basically, and now we go to the bigger picture. The idea is that I want to improve the land model that is embedded within these climate models, Earth system climate model that predict the climate of the future, and the feedback between the forest and the climate system. So if forests grow more, they capture more CO2 from the atmosphere, so they reduce the greenhouse gas effect. Because what forests do now, when they work absorbing carbon, they are healthy, they are really slowing down the pace of climate change and the intensity. So, but it's a fine balance, because if there is too much drought or the climate changes too much, basically the forest will stop doing what they do best, which is growing. And in a way, they will reduce their growth rates, and then their capacity to absorb carbon from the atmosphere will be diminished. And that means that climate change will go faster. So that's why this model, that is land surface model, is called this component that simulate the forest within these air system models, and the feedbacks to the climate and the response to the climate and so on. I want to use tree rings, and particularly these isotopes, and together with the carbon and oxygen, and also the ring width in a way, to improve this model. So if we can, trees will tell us how they have responded over 100 years to these environmental changes like the climate change itself and also the increase in CO2 in the atmosphere, which is in a way a trigger for more photosynthesis at the same time. If I can really teach this model how the 20th century has been for this forest, then I will be more confident in the projections of the response of these trees to the future. So, and their feedback to the entire planet. So, that's basically the big scientific challenge I am working. And then working with ancient trees is one part of it, just a small part, I would say.
I want to talk about the land surface model and this specific project in a second, but I just want to ask you some foundational questions, just for my own knowledge, but also for our listeners. Can you tell us what the critical zone means? What is the critical zone?
Yeah. So, in a way, if we see the planet, it's like a ball in a way, and but it has different layers. The first layer is the atmosphere. It's the envelope of the whole planet that make the climate conditions suitable for life. And then we go down. There is the planet surface, actually where life occurs. It's just a very very thin layer in the surface, so it's from the top of the canopy of the trees to where the more or less where the roots of the trees reach to the bedrock basically. So when you compare it to the depth of the atmosphere, the depth of this layer that can be sometimes from a couple of centimeters to 40, 50 meters perhaps, and then you have the mantle of the planet and the core. So those are big, big, thick, very thick layers. But actually, life in the planet is really thin layer from the top of the canopy until the bedrock, and that's the critical zone. It's critical because it hosts life and all the processes that occur, the interaction basically there, and the biosphere lives there, we live there, and we do all our transformations there basically, and we affect mostly the upper layer, which is the atmosphere as well. That's why it's a very thin and fragile layer of the planet where life occurs.
I just have one question of clarification. So, the critical zone that you're talking about is also called the terrestrial critical zone, is that right?
Yeah, that would be the terrestrial critical zone in a way. But it's not so
And
terrestrial because it also has the canopy, which has a small part of the atmosphere in a way.
right. And then you say that it goes beneath the surface to where the bedrock is. Would that also include the ocean or no?
No, just the terrestrial part.
Just the
Uh,
terrestrial
yeah,
part.
the
Okay.
ocean is different because life can be at very big depth. It would be in the ocean would be basically between the surface of the ocean a bit higher where birds fly. That could be the boundary layer, which is called where the marine influence, the height of the marine influence on microclimate in a way, which can be 100 meters, 200 meters, 700 meters more or less, down to the bottom of the sea and a bit further down probably as well. In a way, in the surface of the bottom, there is life, but probably also a bit further down, perhaps.
With all the climate science data that's out there, why do you think there's so much resistance to climate science?
Well, it's because I think between science and the reality, there are beliefs. And sometimes that filter in a way it's just very strong, very important, and people has very short-term interest, and very in general human society is very self-centered and not too altruistic. And I think in the configuration of the world today basically it's when you talk about countries, everyone is thinking how their country is going to do better than the others and so on, and then no one is thinking in our children, in our future. No one is doing anything for the generations to come. So it's really not thinking that, it's just thinking for me at this time. It's all what matter. There is no past, no future, it's just now. And it's part of the globalization, the current trajectory that we have, I think. So is the planet. I guess is a bad idea that spread all over the world, and and now basically we are just thinking in this wrong mindset and really not thinking in the future and not thinking in others. And now it's becoming even worse. So we can have the best science, and we might still take the wrong choices. But I guess all we can do with science now is to do our best, because there will be some people, some smart people that will take that information and can make all the difference. That's, I think, the hope. That's why we do it. That's why we apply science, not just a sport or an intellectual challenge. I think it's because even when the mainstream is not doing anything, but there will be some people, some communities, some kind of people in some part of the world that will be able to use that, in a way, science knowledge to really make a better future and perhaps steer a bit the trajectory that we are having. So that's part of why we do what we do now.
I'm really curious to get your opinion on what you think of carbon pricing, carbon tax schemes that are taking place in the world with governments, corporations. Do you think that it's really effective? Do you think that it's part of building a better future, what you're talking about right now?
I am very skeptic of all these kind of attempted solution to offset carbon. It might work to extent, but in general, I think at the state of the planet now, it's like we are selling a debt, because ecosystems are just recovering from a lot of destruction in the centuries ago. And then we are selling part of this recovery so others can continue emitting, usually the rich countries and the rich companies. But still, that recovery of the ecosystem, it's just a recovery to a level to their net zero. It's just they are just going from negative to positive, and we are already using that recovery to sell it to emit more. Because in a way, what I mean is that we did a lot of emissions by cutting the forest in the past, and now this forest, let's say if the forest had 50 tons of carbon stored, and then the forest now it has 20, let's say, but it's capturing 1 ton every year. So you say, okay, we'll sell this ton per year so others can emit there, but I'm still short 30 tons in order to just recover the whole ecosystem. Now, if the ecosystem it's at full capacity right now, and you sell what the ecosystem is storing, you can say, okay, then it makes sense. But in general, these things basically just accelerate emissions, because the rate of deforestation is just huge. Will undo anything you can do with that, I think, with the offset. So I think it's a better solution is to really stop deforestation in many areas. Whilst you can use these offsetting schemes to reduce deforestation, I don't think it's that effective. It's a very complicated system because people need to eat in many of these places where the forests are being cut near the Amazon, or, but I guess also industrial. It's just the voracity of our industries in a way are not gonna solve the problem. I think what we have to do is just to degrowth. It's the only way, because the resources are finite, and just we cannot make more forest than what there is now. I mean, or we cannot make more ocean or put more fishes in the ocean than there is now. So it's I think it's very difficult to find a unique solution. But I think it's more effective in a way if we go from grassroots or bottom up as well. We need these top-down solutions, like incentive from government for industries, but we really also need to push more from bottom up to rebuild nature. So then is where I come to one concept that I have been thinking about, and with a particular community near where I grew up back in Chile as well. We have been developing, and it's renaturalization. We call it. It's like rewilding, but in a way, it's since we built our first civilization, we have been trying to tame nature. And then is the Anthropocene, where we are now a force that steer and dominate the force of nature of the planet. So we are such a strong force, but in contraposition with nature. And the idea of the renaturalization is to work with nature. So then some people call it restoration, but it's not restoration, because restoration is try to bring a system back to how it was in the past, but that's not possible now with climate changing. at this speed. So you have to, in a way, work with nature. So it's really to work with together with nature to go fast and let nature decide. So that you engineer certain part of the system, but nature does a big part of it. And I think that's the sort of initiative that we need from grassroots that I was talking before.
I like this idea of renaturalization that you talk about. I saw actually a really cool documentary. It was in Brazil, somewhere in the Amazon region, and a group of Japanese immigrants immigrated there about 100 years ago. And the area that they occupied was completely eroded. And what they did was they used ancient Japanese techniques to regrow the environment and understand how all of the plants and trees interact with one another and how they help one another and how the insects help. And so they created quite a lush environment that otherwise would have been barren. So I was really fascinated by that. And I forget the name of the person, but one of the elders of this community is now actually sharing his knowledge with other communities. So when you mentioned this about what's going on in your community, it just reminded me of that story.
Yes, and it's also an idea that applies to multiple levels. So if we renaturalize a catchment or a basin, what we do in Chile basically is to basically you fenced an area of the catchment and you plant some species that are growing there and you plant some species that grow further north in a way because we're in the southern hemisphere, so it would be equivalent to further south, more drought adapted in a way in this place because those species are going to be winners in the near future. So if we just plant a species that grow right there now, they are going to die out in the future probably. So we plant chances in a way, but nature will decide which of the species that live now there will survive, but we are sure that we are betting on the ones that grow further north, are drought adapted. When drought comes to this place, these species are going to thrive. So then the system will have the elements to rebuild. It's like migrating the ecosystem that is further north, that is adapted to drought, putting it south. But instead, we do it together with nature. We put the plants, but nature is the one that grows it, you know? And then, in a way, you have a system that is in balance with the climate and then produce water. The hydrological cycle is it's natural for that climate and then you get this excess of water that you need for drinking water or for rivers to still be alive. That's the view in a way. So it has we look towards the future, but the beauty of this is that you can in a way renaturalize the planet. You can renaturalize regions. You can even renaturalize ourselves to learn to live with less technology and more close to the land, and then that touches to the other ways of living, which are more traditional, for instance, and a mix in between. So that's why it's a concept that I like it, and also it has precedent in the past. If you look now, you were talking about the Amazon. Now with lidar, with this laser radar technology that can see under the forest, we are discovering that big part of the Amazon that seems to be for us like very pristine were not. There was a civilization at some point there, and then nature took over. And if you look at the temple of Angkor Wat, for instance, you see that there are trees growing on the temples. They are just covered, or the Mayans. So it's really nature comes back, and it's a very very fast process. I'm surprised. Sometimes in almost 10 years you can rebuild the basis of a forest. It's a very fast process. But yeah, you have to work smart. You have to work with nature. You don't take the decisions. You don't put just one single species. You put a set of species, and then nature will decide what it does, and it adjusts, and the ecosystem that is in a way in equilibrium with this climate will emerge. So that's the way how I think you can scale it to ourselves, to the land where we live, and also to the planet. So we definitely need a bit to rewild the planet in or to renaturalize it in many ways. So one idea that I have been bringing, because usually as a climate scientist you bear just bad news, But it's my answer to that. I mean, what is the solution that I propose as a climate scientist? And my concept that has emerged is this idea of renaturalization.
It's a smart idea, and it's really encouraging to hear that forests have an ability to recover. For my listeners, what are your thoughts on our conversation? How is climate change impacting you and your community? What's being done locally to help the environment where you are? I'd love to get your comments. Just DM me on Instagram at the Stumbling Spirit. Jonathan, you received a 1.5 million euro grant from the European Research Council to do research. This is what you're talking about right now on the long-term consequences of altered tree growth and physiology on Earth systems. This project started in 2022 and it goes until 2027. It's called CATIS. Can you talk about this project and what you're doing at the moment?
Yes, I go back to the very simple idea that healthy forests really help to reduce the speed of climate change, the speed and the magnitude of climate change. So, what happened when we alter the forest? When we cut them down, when we change the climate, and now there is more drought where there should not be drought, or the droughts are more permanent, or just too warm for trees to grow. So when forests cannot thrive anymore, what happened to the earth system? And that's just the simple question. And with this project funded by the European Research Council, which is really is the dream of any scientist, is to have your whole team just to answer a question, a scientific question for 5 years, and with all the money and all the prestige that it brings. I think it's a big challenge. To me, I feel very humble for this because it's a big responsibility and also a big opportunity in a way to bring change and to really advance science, but also bring positive change for life on earth. And these wonderful beings are like ancient trees. So I think in my ancient trees, what can I do to help them? And this is the way how I can help them, doing my best science to answer questions that are going to be relevant or that are already relevant now, and that will bring these new ideas to these really, really complicated problems. But sometimes the best ideas are very simple. And I think that's where I am steering. I mean, trying to answer this very complicated question with models by improving a model, an air system model, but then also trying to bring a bit of hope with fresh ideas on how we can act, and also to demonstrate that forest or ecosystems, in a way, forest ecosystem really, really rebuild very fast when we help with the right tools or the right mindset.
You mentioned earlier that part of your focus, or the primary focus, I should say, is on the land surface model, which is also called ORCID. Can you describe what this model is and why it's important?
Yes, basically, some 30 years ago, the climate models, for the first models that represented the climate of Earth, were just the atmosphere and the ocean. The land was not represented. But then there was a problem that the land really affect the climate. So then there was a need to create a representation, a new model in a way within this very simple model of ocean atmosphere, which were the general circulation models, they were called. You have the ocean and the atmosphere. And then the land was needed to represent. So we represented the land with this land surface model because where the terrestrial carbon cycle occurs, so the capture and release of carbon in forest ecosystem or agricultural ecosystems, and also the water cycle, all this the continental balance of precipitation, evaporation, and river runoff, all that affect the climate as well. So basically, this component is the one that does everything in the global biogeochemical cycles, in a way, the water, carbon, nitrogen, and also we represent how we manage the ecosystem in the land surface. So forest, agriculture, cattle, and all the management that we do. Now we are starting to represent cities as well, like represent how cities affect the atmosphere above them. So That's where we do all that. And that model is where forests are and where I work in forest. So that's why I work in that part of the model.
And it's my understanding a constrained study that focuses on biomass growth, water use efficiency, and root rings. So, can you describe what they each are and why you are focusing on those areas?
Yeah, so finally, when I talk about all these complicated things, it boils down to two processes. First is biomass growth, how much trees grow as CO2 increases and climate changes. And let's say if you have more drought, but you have more CO2 in the atmosphere, plants tend to become more water efficient because plants, what they do, they lose water by transpiration. When they open their pores in the stomata, in the leaves, they lose water in order to capture CO2, molecule of CO2. But since now there is every year there is more CO2 in the atmosphere, there are more molecules. Plants need to open their pore for less time, let's say, to get the same amount of carbon. Let's say in the past you had to open for, I don't know, 3 hours to get X amount of molecules. Now, since there are more molecules of CO2 in the atmosphere, you open less time. As a result, you save water. And that water, where it stays on the soil, on the ground. It's not transpired to the atmosphere. And that is the way how plants start to change the water cycle. If you can quantify that better, that water saving, that will impact the amount of water that flows into the rivers and so on. And then the amount of water that is available to evaporate and to make, let's say, moisten the air and to make rain on land. So it really feedback in many processes. That's why I focus on the water use efficiency. And that is basically made with this carbon isotope that I taught before in tree rings. That tell me about that. And the width of the rings tell me about the biomass, the amount of biomass that is being captured in a way. The water use efficiency basically links the carbon and the water cycle. And the beauty is that with the true rings isotope, you can really track down back to the whole 20th century, let's say, in many parts of the world. And you can use that to improve what the model does as a response to increasing CO2.
I'm just curious, why are you looking at the root rings versus the trunk rings?
Yeah. So the other axis of importance. So I was talking to you now basically just what we see above ground in the forest. But forests have a hidden half, which is below ground. So it's what happened in the roots, where half of the carbon, more or less, that the trees capture by photosynthesis goes. And so if you again sum up it all over the forest of the world, it's a lot of carbon. And it has a huge impact into the atmosphere as well. So basically, we know very little about that. And I think that's one of the biggest mysteries now in forest ecology, at least, how we can, in a way, better understand how carbon is being allocated to this below ground component. That's why I use tree rings as well, because the coarse root of many species have rings. So you can have the same thing that you have above ground, you can have it below ground. So I can know the rate of growth of the root system as well. And I hope to link that to the fine roots because basically the tree is like inverted in a way. We have the leaves and the branches, but below ground we have the coarse root as the branches, and the equivalent to the leaves will be the fine roots. So where most of this carbon is allocated to grow this fine root, the ones that basically capture nutrients and water for the tree. And so the forest might be doing things that really don't know below ground. And the rings will allow us to go back a century again. So it's really wonderful because the measurement that there are of fine roots, it's very difficult to observe, to measure them, how they grow. And they are formed and they live for around 3 to 4 years, 5 years. Sometimes it's just 1 year. So one leaf is formed, it lives for a couple of years and then it dies. So the fine root do. So it's like exactly the equivalent to the above ground, but the below ground part. And so I hope to really unravel a bit of the carbon cycling of roots, but also with a long-term perspective. So we are studying forests in different biomes. So from boreal in Finland down to temperate in Europe and part of the US, down to tropical forests in South America and part of Africa, and again to Mediterranean system in Southern Hemisphere, and then rainforests in the Southern Hemisphere as well, to try to capture how these different type of forests might be responding in the below ground part, which is one of the biggest mysteries still. So I just want to really scratch the surface of what might be happening there. So I think that's one of the most exciting part of this project, is try to really make a new methodology to look at the what the roots do of the trees.
In addition to understanding what the roots are doing, you are also trying to reduce the uncertainty of the level of understanding that we have now around the carbon cycles. So,
Yes.
can you talk a little bit about that?
Yes, when the thing is that when we use the models that exist now, the land surface model that exists now, they give us like a spaghetti plot to the future, which is like a fun in a way. If we ask this model how the forests are gonna respond from all over the 21st century up to the end of the century, now we know that the whole biosphere, in a way, all the forests in the world are a sink of carbon. So they absorb more carbon than what they emit to the atmosphere. But some models say that it's going to be a source, a big source. Others say that it's going to be neutral, so it will emit the same amount that it captures. And others say that it's still going to be a sink. So basically, the answer is very uncertain. We cannot tell what the forest will do in the future. And the problem of that is that basically this model have been trained with observations like satellite observations and some experiments that are just a few decades long, so 20 to 30 years long. And particularly the measurements of fluxes of carbon and water in the so-called eddy-covariance flux towers are towers where we measure the exchange between forest and of carbon and water between forest and the atmosphere. We measure it, and there is a network around 500 sites in the world. And so we have taken all those observations to really train this model, and they do very well. They simulate, let's say, the current fluxes very well, but when we extrapolate to the future, they just go crazy. So then the answer is like, okay, this is a problem because really the model has been trained in a tiny period of change and it cannot be extrapolated for the future. So what if we train the model in a century? We go from 30 years to a whole century. And that's where true rings come in a way. The true rings bring in this perspective, this century long perspective. And it's in a way a new set of data that allow us to really train the model in a long-term horizon in a way. So it's a time frame of a century. We train the model in a century to predict a century. Of course, the changes in this century that we are going to predict are faster, but we still capture, I think, a fair amount of change all over the 20th century. So it's going to bring a new long-term perspective for these models. And that's what basically we are trying to advance with true rings.
What do you perceive are going to be the breakthroughs from this research? And what applications do you see this modeling being used for?
I think it's basically the breakthrough will be to know if having this constraint, long century long constraint from historical tree growth, in a way, if we apply this methodology to all the models, if we can reduce this uncertainty, how much we can reduce this uncertainty into the model to say it's going to be a source of carbon to the atmosphere, the whole biosphere, or it's going to be neutral, but it won't solve the problem, but it will reduce the problem. So in a way, it will improve the biology of Earth system model, which is the major, I would say, drawback of these models now. The biology is very uncertain. The physics are very well constrained, but the biology not. And I think we are gonna be able to bring first answer to that, to constrain this biology, and also we might be able to untap a tiny bit of how forests are responding to below ground in the hidden half below the ground. So how are they allocating more carbon to the roots over time as CO2 increases or not? Or is that being altered by drought or not? So that sort of, I think, that view to the below ground is also going to be an important breakthrough, I think.
Obviously, I watched your talk that you did at CRU at Norwich University. And one of the benefits that I read, and I'm just wondering if you could speak to it a little bit more, is predicting the future land carbon sink. What is that?
So basically, if I go back to the simple idea I explained before, is that forests, in a way, reduce the speed of climate change. When I say that, basically, I'm saying that forests are a land sink because there is another part of the sink that is the ocean. It's around a third of all the emissions that we emit to the atmosphere now. A third is captured by the ocean, and another third is captured by the land. So think that there is way less land than ocean. So the land one is a very important one. Still, that's a third. Between the ocean and the land, there is 60% of emissions that are not in the atmosphere in a way. Climate change will be way faster if these two sinks of carbon do not exist. So we would be like in a very warm planet now if these two big systems were not doing that. And so the future land sink basically is this capacity of the land part to be the sink. And as I said before, some model says we are going to lose this sink, basically that all the land is going to emit more carbon to the atmosphere than what it captures. And some others that say that basically this sink is going to be disappearing because it's going to be neutral. And others say that this thing is going to increase. With this, and basically, I think having the message of the trees encoded in these models, we can pinpoint a bit into this answer to try to reduce this answer. At least we will know how much the model changes in answering this question. So I will believe more the model basically having the word of the trees on it than rather not having it. So, and I think that's basically how I would summarize this project.
What is your hope for the future of the environment?
It's a very political answer, and I think as never before, the future of our environment as thinking as a planet, really it's in our hands, and things are not looking good. And every time that a new president comes that basically dismiss science, we go decades back because it takes a generation to undo these changes. And we don't have that time. So what I think it's that probably the planet is going to collapse. The social systems as we know them now, life in the planet is going to change as we know it as humans. Our daily life is going to change. So what I think is that basically societies are going to collapse in many places, and in some places nature might collapse too, and that comes to this concept called tipping points. There are some social tipping points and there are some system tipping points, like what happen if there is too much warming or that we enter like an El Nino permanent state, then the forest in the Amazon will die out because it will be just too warm, and then that will bring changes in marine currents and so on. So basically it's really a collapse of the normal function of the system as we know it. So I think the first social collapse we are going to see probably in the next decade, some social collapses. And we are not also at a rate of disaster that we are not going to be able to rebuild before the next disaster comes. And that basically will cause a lot of social unrest and stress, and it will demand big changes in the way we live. And we are far too many now in the world. There are not too many free spaces probably. So that basically it's posing a very big challenge for the way we live now. So the answer is to look for alternative ways where we can be more resilient to all those things, and also hope for the best that The Earth system is not gonna approach so soon one of these tipping points.
You mentioned resilience. What does resilience mean to you?
Basically, I would define it in this case as the capacity to adapt in advance to a very likely set of scenario features. So you are prepared. And that means, in a way, thinking in all the ways things can go, probably from very bad scenarios to the best scenarios, and adjust on time and adjust your life to that, basically. You have some choices and others you cannot choose. I mean, there are some things you can change and others not, but you can change the way you live, where you live, and how you interact with people, how dependent are you on the whole network or the system. So it goes in many ways. As simpler as we live and closer to the land we live, more resilient we become.
I'm really curious to get your answer to this. What do you think is the connection between resilience and survival?
I think to survive, you need luck or resilience, probably. The connection between the two, when you talk about systems, is a very close one-to-one relationship, I would say. You are not gonna survive if you are not resilient, because surviving doesn't mean that you will solve all the problems. It means that you will solve the problem to a level where you still thrive in a way, or you still are alive. But it doesn't mean you are gonna reduce the effect or the consequences of the problem to zero, just to an extent where you can still be keep going in a way. And that basically require a lot of thinking, and especially I think nowadays that's where I connect to the answer I told you before. So it's good to have the best science, because there will be some minds, some people that will be able to use that science and to really build more resilient systems on time. Like this community I was talking to you before about the renaturalization. If they are able to really, in the next 10 years, to rebuild a lot of their forest and live closer to the land, they will be more resilient in the decade to come, in their lifetime, basically. And but then the new generation will have to still to think ahead, probably will learn from this generation to be smart and to think ahead and to do their part for the coming decade. So that's why I think by using the best science we can build resilience and we can ensure survival of our communities.
What are your personal practices of resilience?
Basically low consumption and materialism, I would say, how you could say it's the contrary to being a materialist person. Live with the minimum, consume in a very conscious way. And also now I travel, my travels are long, I emit carbon, I know, but my way to offset it is to, for instance, I don't drive, I don't know how to drive, and I don't want to drive. Since my upbringing was in a region where I used to be moved by horse. Historically, I have very few emissions. I'm emitting more now, but how I offset what I emit now is that I go for maximum impact with my science. I do science for people or science for the planet in a way, what I call this part, which is to think in these ideas of how we can solve problems, and then going back to renaturalization that goes to multiple levels. So well, I have renaturalized myself probably, but I grew up wild. So I grew up in the forest. I grew with very little technology. And I went to live in big cities like now, but I still live with little. I don't accumulate much. I don't drive. And I can still do my things. I don't need to consume a ton to be functional and to be happy enough. And I think that's the way how I renaturalize myself now, going back to the forest. I have a self-sustaining system with solar PV system, with water from spring, and apply all the necessary technology to keep a very comfortable life, but with low consumption and low impact.
There's a lot of integrity in that. So, this simplicity that you speak about, what are the benefits that it gives to you?
I think it's just integrity. By the time I die, I will die with the comfort that I did the right thing and I gave the right fight.
So, If Gran Abuelo could speak, what do you think he would say based on the wisdom of his years?
I think I once thought about that, and I think what ancient trees tell us is it's life on Earth at these time scales is very fragile but remarkably adaptable.
Dr. Jonathan Barichivich, thank you so much for joining me. It was such a pleasure talking to you and getting your perspective based on your expertise, but also just based on your life experience. It really feels like this career, this vocation is really a part of your heart and that you really want to do something beneficial, not only for our collective knowledge, but for the environment. Thank you so much.
Thank you very much to you for the opportunity to discuss about these ideas and to share ideas that I'm sure that there is many other people listening here that is thinking along the same lines and probably have even better solutions for the problem that we discuss. And I would love to hear about that as well.
For more information on Jonathan Barichivich, visit jbarichivich.github.io. Any inquiries about Jonathan's research can be sent to his email address, jonathan.barichivich@lsce.ipsl.fr. Barichivich is spelled Barichivich. Thank you for listening to The Stumbling Spirit, Contemplations on the Path of Resilience. This is Fabio da Silva Fernandez. Join me again next week for another episode of transformative stories and beneficial practices to guide you on your wellness journey. If you wish, you can follow and DM me on Instagram at The Stumbling Spirit. Until next time, take a deep breath and another step forward on your path of resilience.